In this lecture, what we're going to look at is what else we can do with the gamma function but now we want to do the gamma function of negative numbers. So previously, what we did was we defined the gamma function. We said that the gamma function for a number p was the integral of x p minus 1 e to the minus x dx. And what we also found was we found this recursion relationship where if I take gamma of p plus 1, then that would just be p times the gamma of p. So if we figure out one, we can pretty much apply it to others, but we only really looked at that in terms of p if it was a number greater than minus 1. Or basically a number greater than minus 1. So the question is, how can we now apply that to any number? If it's a negative number, a positive number, fraction, any real number, how can we apply that? One thing we can look at is, why don't we switch this around and say gamma p is 1 over p times gamma p plus 1. If we kind of turn around the recursion relationship, then now what we can do is we can start it with a smaller number and base it on a larger number. So if we figure out what the larger number is, then maybe we can work our way down to smaller numbers being negative numbers. So we'll start slow and basically say that we want to, basically base these numbers on numbers where p plus 1 is greater than 0. So we want to base our negative numbers on a positive number, which are much easier to work with. For example, the gamma function of negative 0.3, I would write as negative 1 over 0.3, so that's the p, gamma negative 0.3 plus 1. Okay, so if let's say I want to write these in fractional form, and I have negative 1 over 3/10, gamma positive 0.7, or negative 10/3 gamma of 7/10. Okay. Okay, so once we've done that, then we could look at an even smaller negative number. So gamma of negative 1.3 would be, if I would put this in as negative 1 over 1.3 gamma of negative 1.3 plus 1. So gamma of negative 1.3 is equal to negative 13 over 10 times gamma of negative 0.3, which we just worked out. And so gamma of negative 1.3 would be equal to minus 10 over 13. Now I've already worked out what the gamma of negative 0.3 is, and so that would be another 10/3, negative 10/3, times the gamma function of the fraction 7/10. So if I put that together, gamma negative 1.3 is equal to positive 100 over 39 times the gamma function of 7/10. So again, I still have to figure out what that base number is. I still have to calculate what gamma 7/10 is. But if I did, that's the closest base number I need. I can just plug that in, and now I can have the gamma of this negative number. I can have gamma of negative 1.3, gamma of negative 2.3, gamma of negative 10.3. I could basically work my way up. And all of it would be based on the gamma of 7/10, which I still have to work out. So if I think about it, if I go back to my original formula, that gamma p is equal to gamma over p plus 1 divided by p, then if I let p go to 0, so I'm not going to set p equal to 0 yet, I'm just going to allow it to go to 0, then that would mean that gamma of p plus 1 would go to the limit of gamma p, I'm sorry, not gamma p, which would be gamma 1. And gamma of 1, if you remember, that gamma of n plus 1 is equal to n gamma of, so that gamma of n plus 1 gamma of n plus 1 is n factorial. So in this case, what do I have? But I have n would be 0. So gamma of 1 is 0 factorial, which is just the number 1. So that means that gamma of p as it approaches 0 would be basically going to 1 divided by 0, which is essentially infinite. So this gamma function that we want to get to, if you want to figure out what gamma 0 is, basically what you're doing is you're asymptotically going toward infinity. So the shape of the gamma function was as your number p approaches 0, then the gamma function is going to blow up asymptotically from there. Okay, so let's keep considering what else we can do with the gamma function. And so let's start with the gamma function of p when it's equal to 1/2.